Hi everyone. My name is Sai. I'm a principal architect with in the platform team with Allscripts Healthcare. And in this talk, I'll actually be covering what is infrastructure as code. We'll actually look at some popular tools such as Terraform, Azure Resource Manager templates, and some recently released Azure BICEP as well. After that, we'll move on to IAC code abstractions using modules, its advantages, and some example config. And finally, we'll talk about some continuous integration and continuous deployment pipelines for IAC code. We'll talk about some design considerations of these pipelines and a simple workflow. And then we'll close off with enabling IAC scanning on the workflows as well. So what exactly is IAC or infrastructure as code, right? It's a management of infrastructure resources such as virtual machines, networks, storage accounts, and other IaaS or PaaS services using code. There are some significant benefits of deploying infrastructure using code, especially if you're working with large-scale deployments. We'll go through some of these benefits in this session. So similar to application code, IAC can be version control using tools such as Azure DevOps, Github, or any other source control tools. And one must be wondering, like, why should I go through the pain of writing code when I can go to the portal and just click the buttons, click next, and then within a few minutes you have resources? Well, there are a lot of advantages of using code, and one of them is that you can actually have, since it's code, you can actually validate and test out, ensuring that your deployments are successful each time. There's no issue. So if you have a multi environment for an application, you can actually ensure that each environment, like the dev environment, the QA environments, everyone, all of them are consistent and they're not kind of different, and there's no drift between configurations. One of the biggest challenges that we have is in large multi-scale environments, consistency, like I was talking about. And we can't, and using code, we can guarantee that each environment is consistent and it matches the approved architecture that we started with. But if you're going through manually and deploying stuff, there's always a drift, and we can't find a certain value, or we kind of miss to kind of configure a certain thing, and now we have a different environment between dev and QA. The other biggest, and just imagine, like, if you were to build out like 5 different environments consisting of multiple resources, various configurations, like you have 10 and 20 or 15, 20 resources that you're going to deploy, and you're doing all of this by hand, it's going to take you forever. But using code and using some automation that we'll talk about later, these deployments can be, these resources can be deployed faster and on demand, which will help us save some cost and also some time. Like, for example, you don't need to have a QA environment when there's no QA testing happening. But if you're going to do this by hand, since it's a very, very lengthy process, you will say, I deployed it now, I'm just going to keep it on for the entire time and maybe just pay for it. But then if you're doing everything by code, you can delete it and then rebuild it on demand only during the QA testing process. You don't need to keep it always on. So you also save some cost as well in that scenario. As all definitions are through code, reapplying it will eliminate any drift, cause you to undocumented changes. Like that's one of the worst nightmares to have. Like, production is at a different configuration, the dev environment is a different configuration, and all of this has happened because someone made a change and they didn't document it. But if everything was through code, each change is documented, and even if there's something undocumented, the next time you reapply the configuration, everything just gets back to its original state. There's no differences. So the popular tools used for the popular tools in the space includes Terraform, which is an open source tooling, CloudFormation from AWS, and ARM and BICEP from Azure. So we'll talk about Terraform to start off with, right? Terraform is an open source platform that enables deployment and management of infrastructure resources across various platforms. It's declarative and easy to understand language. Terraform maintains a state file that can be used to audit and track changes across the infrastructure, which becomes extremely important in highly regulated industries. You can use Terraform across AWS, Azure, and other cloud environments, as it has multi-platform support. As a Terraform user, it's very easy to get started with Terraform. Firstly, we need to identify the scope of the infrastructure, such as destination environments, resources that need to be deployed. And then using your favorite IDE, you can author the code. And then you can use Terraform init to initialize the code. We can validate the code by running Terraform validate, the validate command, which checks for any code errors. Then we run Terraform plan to generate a plan of what Terraform intends to do in the destination environment. So it basically generates out a large document which tells hey, I'm going to go deploy this virtual network in this resource group. I'm actually going to change subnet value to so and so. I'm going to deploy the virtual network. I'm actually going to deploy NSG rules. I'm going to deploy a virtual machine, and tie everything together. It kind of gives you a very structured plan, which is very easy to audit and approve during for any change management scenarios, right? And then the last thing is the Terraform apply state. So when you and then we run Terraform apply to deploy the code. And I think by now you would have guessed it, right? Terraform delete will delete all resources that's defined in the code. So if you want to get rid of a resource, all you need to do is run Terraform delete with the same source code that you have. It will review what is defined. It will go clean up the destination environment, and it'll kind of save you cost as well in the scenario. As you can see, Terraform is simple, easy, and a very powerful tool. One of the only drawbacks of using an open source third-party tooling such as Terraform is that there might be a considerable delay when they onboard a new feature. Like, for example, if there's a new service available on Azure, there might be some time or there might be some delay that it's onboarded to Terraform. Other than that, it's a fantastic tool, and I think it's very easy to understand, and it's very powerful. The next tool that we have, and we'll talk about, is Azure Resource Manager Templates, or Azure BICEP. So ARM templates is an Azure native service. Like every IAC, it's declarative. So it has a declarative syntax, but it's JSON based. As my good friend Kyler mentioned yesterday, JSON is yucky. No one likes JSON. But as it's native to Azure, it has built-in validations which occur during the deployment process, ensuring that you have successful deployment each time. Unlike Terraform, which you can't really guarantee that unless you start the deployment process. And unlike third-party tools that rely on APIs for deployment, ARM or BICEP is very fast and reliable as they're platform native. They baked into the platform, they're very fast, they're very reliable compared to other tools. While open source tooling might take some time to catch up with newer releases, cloud natives IAC such as ARM and BICEP have the latest features latest features readily available as they are platform native. Like if you have a new service on Azure or a new feature on an existing service, it's already available in ARM or BICEP because it's baked into the platform. So BICEP is more recently released version of from Microsoft. You can consider it something like an abstraction of ARM. The good thing is it's not JSON. It's easy to author when compared to an ARM template, and it comes with all the advantages of an ARM template. And to deploy an ARM template, so unlike Terraform, to deploy an ARM template, you actually can use the command line tools from PowerShell or AZCLI, or even the portal to store and deploy templates consistently across your environment. Now that we've covered some IAC fundamentals, we know that using IAC, we can consistently deploy infrastructure reliably and fast. But what do I mean by IAC code abstraction? By IAC code abstraction, I mean that the consumers of the code are able to define a subset of the values necessary for the application or service to function properly. All of the other parameters are predefined on the organization based on the organization's best security practices. So the major advantage of planning IAC deployments using this approach is that resources being deployed are predefined with best practices and secured by default. We don't need to do any additional configuration checks after the resources be deployed. Mainly to achieve this, we use IAC modules. So what exactly is a module? Module is a collection of code that is shared across one or more applications across an enterprise. And within an enterprise, it's best for these modules to be stored in a centralized version control location that's accessible to everyone and can be referenced by various applications. So I'm talking about a scenario where you have a large platform, you're supporting multiple enterprise applications, and as a platform team, we have these challenges. Like we have like 15, 20 applications that want to deploy resources, and all of them have their own design, have their own application architecture, have their own resource architecture, and all of them are unique by themselves. But they all want to deploy same resources like virtual machines, storage accounts, network, and so on, right? So it's the best thing is that we centralize these modules, we version control them so that every application can access them, and we actually update the versions of these modules based on the developments of the cloud provider, and the downstream applications can reference the latest version. So if you have some improvement in a storage account, or if you have a new release of a virtual machine that supports additional functionality, we can make a new version of the global module and then call it the latest version, and then the downstream applications can actually tag to the latest version, and they get access to the latest for the later functionality of the code. I think like one of the other presenters covered in yesterday's session, where there are a set of pre-approved services that are defined for, that can be defined for an organization from a cloud provider. These modules can represent a approved set of cloud services with predefined security configurations that enables teams to move faster and reduce review cycles. So what exactly I mean by this is that these modules are, so firstly, these modules actually represent the services approved for use within the organization. Like some services we may not even be able to use because they don't have certain compliance parameters, or they don't meet our security requirements. So the application teams are actually are kind of guided to use the existing modules that we have built for them, because those are approved services. And the advantage of this is that these modules now also have predefined values set to them, like they're already secured by default. The application teams don't need to think about security. They just have to use these modules, and the resource actually is deployed securely. So these modules not only contain code, they also contain predefined values, as I was talking about, and they cannot be overridden by the downstream consumer. So the application A, if they're trying to consume a storage account module, they can't change predefined values. So, and you can see in this slide, we have multiple modules such as virtual networks and virtual machines and storage accounts. And all of them are like cross-referenced across applications and environments and so on. So what are the advantages of using the modules? Major advantages of using the modules. First thing is it's a reusable code. It eliminates the need for application teams to rewrite the code for each application deployment. So all they need to do is reference the module and pass in the required parameters, and that's it. They don't need to think about what all the hundreds of lines of code that they need to write. They just need to pass in values for it. Centralized resource definition. It helps to organize code using centralized modules within deployments. Faster deployments. As the code is tried and tested, it enables teams to move faster, and they don't need any additional reviews by security or platform teams, because these modules are already pre-built and designed to be secure. Reduced error. The main thing is that when using modules, it provides a layer of abstraction from other resources, hence enables to reduce possibility of errors during a resource update. So if suppose you're going and updating all resources, you actually can update just the module and not cause an impact other side services that run within the application. And consistent configuration. Resources have standard configuration across all environments and all applications within the enterprise. One can have the confidence that a resource definition, that resources definition across organizations are consistent, which means that storage accounts in app A have the same security configuration as application B. There's no inconsistency. All of them have the same settings. All of them have, the TLS versions enabled. All of them have diagnostic settings, auditing enabled. All of them have the same exact consistency. This again helps the teams to move faster. The most important one from my point of view is that modules can be built using secure best practices, which can be automatically applied to all environments across all applications that use them. Basically, they're secured using best practices, and that's by design. So I have an example of what a module looks like and how it's going to be consumed, and we'll take a step back and we'll kind of explore the old way versus the new way. So in a non-module world where you have a complicated application being deployed into Azure or AWS, and we have multiple resources like as we just spoke about, right? App teams are consistently looking for guidance on what values to use for security fields, like what should I have for the TLS version? What should I do for the firewall? Should I set it to allow? Should I set it to deny? And they may not really know. And they don't really know what to put and what IP should I allow on the firewalls. Like what should I really do in the network rule set? Should I enable the infrastructure encryption or not? Should I enable public broad access or not? So all of those are open questions. And just multiply this by all of the resources that you have to deploy. So for storage accounts, for key vaults, so SQL databases, these questions keep coming up time and again. And we actually spend transactions and cycles of time to actually review the code, help them or guide them through setting this up securely, right? And now multiply this with all the resources. It's going to take up a lot of time. This not only introduces confusion into the process, but also creates a scope for inconsistent configuration. Like for some storage accounts, we might have diagnostic enabled. For some, we may not have diagnostic enabled. So because it's all manual, it's all transactional, it's on a call, or it's on a working session. Some configuration might get missed out, and we'll start to have inconsistent resources deployed across the platform. Now, since that's the plan, now we have to actually plan to audit them, which again takes time and then takes money as well. And the worst possible outcome is the business team starts to see challenges in adopting cloud services. Now they're going to start saying that every time I want to deploy a resource, I have to go through like 10 different reviews, multiple points of view, and then everyone has had their own opinion, and deploying a simple application is just going to take forever. But now if you consider a module, the world with various modules, if once the application team has an approved architecture and they're going to go start deploying into Azure and AWS, all they got to do is reference the module in the global modules that are there in the centralized modules. So if they want a VM, if they want a virtual network, if they want a key vault, if they want a SQL database, whatever they need for that application, they just have to reference the code in the global module and then call it. So as you can see, like this is an example of a storage account and some default values. So in the storage account, we see that the firewalls are set to deny. So it's not publicly exposed to the internet by default. Unless you're on a certain IP or a certain subnet, you will not have access to the data in the storage account. Encryption is turned on. If you're in healthcare or in other highly regulated organizations, you have to actually have encryption as part of compliance requirements. Encryption is turned on by default. The teams have no choice but to keep it enabled. They can't override these parameters. TLS versions are enabled to use 1.2 or the latest version that the cloud provider supports. And then we also only enforce HTTPS traffic. So these are some defaults that we push for the application teams to use, and they don't have a choice, or they don't have an option to change them, and ensuring that the resource actually securely deployed. Additionally, the module also could have other resources. Like in this example, we see that we have diagnostic settings enabled. Again, from a HIPAA compliance point of view, you need auditing, you need diagnostic logging enabled, you need all of those stuff enabled. And again, the application teams have to go through cycles of time, how to enable it, figure it out, and then have code returned to it. But we are presenting them a module and say, hey, this module gives you all of that stuff baked in. You don't need to think again. You just use this and you have a resource and it's secure. You are happy with the faster deployments. I'm happy that it's secure. And then you have a successful deployment, right? That's the main intention of this. So on the left-hand side, we see how the consumption of the module will look like. So the application team, we just have to write like 5 or 10 lines of definition. But whereas on the right-hand side, the module definition is like 20 lines. It has all the parameters. On the left-hand side, all they just got to do is provide the storage account name, provide the resource group, provide the location, and then that's it. Like whatever they need for the application team, that's it. And everything else is built in. This is a major advantage. It saves time, and it actually improves the resource, the security of the application overall as well. So far we've spoken about IAC, the infrastructure as code, some modules with security defaults. And in the last section of the presentation, we'll actually talk about CI/CD pipelines and how using pipelines we can automate validation and deployment of IAC code. So what exactly are pipelines? Pipelines are a series of tasks that are tied together in a sequence to perform a certain action. These might be called differently by the tool that you're using. Azure DevOps calls them build and release pipelines. GitHub calls them action. But eventually all of them do the same thing. They actually run a series of tasks to perform a certain action. And in our scenario, the action is going to be validation of your code and deployment of your code. And the tasks are going to be like running Terraform validate and Terraform plan commands. That's how we're going to kind of segment these out. But before we go there, we'll talk about some design considerations of pipelines. So let's start with the least privilege. Pipelines need access to perform deployment tasks, right? So now, but they shouldn't have access to everything. They can't have access to the subscription. They can't have access to resources that they don't need access to, because the subscription might be hosting other services as well, right? So we should go with the bare minimum privilege as possible, which is the smallest scope possible, maybe at a resource group level, so that the scope of the access is to the smallest possible on the subscription. For an example, a pipeline of application A in the dev environment should not have access to the QA environment. We want these pipelines to be segregated and segmented out so that there's no there's no crosstalk between environments. And I think one of the earlier discussions, I think there was a question asked to how do we scale the least privilege? So the approach that works best in our scenario is that we started denying scary permissions. That's what we called it. Like we can't go ahead and just give a bare minimum privilege. So we can't give contributor because it has too much access. We can't give owner because it has much more access. But at the same time, we can't start with something very, very small and then keep on adding it. And that again takes cycles of time and, delay in overall deployment. So what we said is like, you'll have contributor access, but then we'll have it tweaked to just remove all the scary permissions. Like you can't delete any resource. You don't have data contributor access. You just have access to create and modify resources, and delete is only given on a need to basis during, for any approved changes and so on. That's one way that has worked for us, and it's been the least kind of resistant way for us to start off with least privilege. And again, the privileges are to the minimum scope. So it's only the resource group level, and only if required, we go much higher than that, maybe multiple resource groups and stuff and so on. But it's never at a subscription level, because a subscription can actually host multiple environments and multiple applications as well. The next big thing about pipelines is approval gates. Pipeline tasks can be set with approvals. So one may be wondering, like, so anyone can go run the pipeline, right? It'll now they can wipe out an entire production environment because the pipeline is run. Not really. If you have approval gates, what means that even though a pipeline is triggered, it will not execute unless it's explicitly approved. And we can go further and say, we'll let the pipeline run, we'll let it generate a plan or do a certain prerequisite tasks, but it will not actually apply anything to the production environment. And that's where it'll say, I need an additional level of approval or an additional set of eyes to review what is happening and then approve it. So we have a flexibility of, okay, at least we know a plan is generated, and then we can have like a change manager or someone approve the actual execution of the apply, wherein the deployment happens to production environments. And in non-prod environments, where there are a lot of changes, we also can script to do an auto deployment based on the plan generated. So it's a non-production, it's not critical, it's not going to cause an impact to the live application. So for example, if the Terraform plan indicates it's only going to be adding resources and not delete anything, then maybe we can actually have it auto deployed without having any additional approval checks. The main intention behind taking this kind of approach is that it actually enables for faster turnaround times in non-production environment. So the worst thing we want is in non-production, non-critical environment where teams want to iterate fast and then go at their own momentum. We do not want to have additional checks and balances in place which just delays them. So as long as the plan is safe, it's not going to delete or wipe out the entire environment. We just say, it's going to be auto approved, just go ahead and deploy it, and you can deal with the changes because it's on production environment. And finally, the biggest takeaway for me is blast radiuses. So now that we have code and pipelines and everything, what happens if suppose something goes wrong, right? We are humans, we all make mistakes, and what can we do to minimize the impact? I don't think we can do much to fully reduce it, but then but what can we do to minimize it? This is where blast radius comes into picture. Basically, the idea is not to have one large pipeline for one application, but break it up into manageable chunks. Something like segment out the application into multiple layers, like network layer, the front end layer, the data tier, and the compute or the logic layer or something like that. And then you actually have a pipeline for each of them. And each of them have individual permissions, kind of following the least privilege approach. So the network pipeline will not have access to delete or edit VMs. The one which actually has a front end will not have access to change maybe the database tier and so on. That way, even if suppose something were to go wrong, it's limited to just that scope of the pipeline and not to the entire application. While there might be still an outage, it's not that you have to redeploy the entire application and take a much larger outage. It's going to be a much smaller window, and we can quickly recover from those kind of outages, or may fail out to DR in that scenario. But then the impact is much smaller compared to having the entire environment wiped out. So these are some high-level design considerations for pipelines. The next is going to be a simple validation workflow. In this, basically, this is going to take you through a process of like of what happens when a PR is submitted. A PR is nothing but a pull request. It's a request to make a change to the IAC code in the source control. And based on the pull request, validation jobs are kicked off. So what do I mean by validation jobs? Validation jobs contain Terraform validate and Terraform plan commands that confirm that the code checked in is valid and can generate a valid plan. This does not guarantee a successful deployment, but it definitely confirms that the code and syntax are not faulty. Like it's correct code and there's no issues with the code. We also can go to more detail by running Terraform tests that validate a successful deployment. However, for this session, we can't go to that level of depth. We just keep it at a very simple level. We just do simple validation, a plan, and if everything looks good, the plan is then reviewed by a human being, and then it can be merged into the development, into the deployment branch. This is a high-level overview of a simple workflow. In the next section, we'll actually look at how we can do IAC scanning. So I'm sure all of us might have heard of application code scanning and to find vulnerabilities and see if there's any faulty libraries we're using and so on. A similar thing can be done for IAC as well. IAC code can be scanned for vulnerabilities with the current configuration. And in this scenario, vulnerabilities include kind of misconfigurations of resources, like having NSG rules or VMs and stuff put on the internet. Like if you have a RDP port exposed to the internet, or if you have SSH or SQL ports on the internet, IAC coding scans will actually catch them and will actually fail the validation, saying, hey, you're doing something which is going to cause a security impact to your organization or to the application. I'm going to fail the build. I'm actually going to fail the validation, and you have to go check it out. The workflow looks very similar to the previous slide, but with just one additional step wherein IAC code scanning. This step consumes the state file and generates a report with all the issues in the code. Based on the tool that you're using, you'll be able to set thresholds and fail validation checks. If a certain number of high issues have been reported. We also can categorize and prioritize the issues based on organizational requirements. For IAC scanning, we primarily have two options. If you're using Terraform, and you can use third-party tools such as Prisma Cloud or Wiz or any other security or code scanning tools that actually scan your Terraform plan for any vulnerable configurations. But if you're using platform native tools such as ARM templates or Azure BICEP, you'll be able to use services such as Azure Policy to validate your deployments. Azure policies are a very powerful tool. If not use them, please enable them on your tenant. You can actually deny a certain configuration. You can actually go ahead and fix a certain configuration. Actually can make changes to the environment, which can keep your application and your cloud, your subscription secure. And the best part is ARM actually feeds into it. So if you have a policy on Azure, on Azure policy saying, do not enable storage accounts with the firewall enabled, ARM template validation will fail, saying you're actually violating a policy because you're deploying a storage account which is having its firewall disabled, stuff like that. And this validation actually happens during the deployment stage. So once we start to deploy, the validation will fail, and then we know that we have some faulty code, and then the team submitting the PR can go ahead and fix the code, and then they can resubmit the PR. So after that, the plan is merged. The plan is reviewed, and then it's peer reviewed, and it's merged into the development branch. So that's it I had. So to quickly summarize, in this session we went over what is infrastructure as code. We talked about code abstractions and modules, and how to deploy them securely. I showed some examples. All of these examples work for both Azure and AWS as well. And hopefully, you found. Hopefully, this will help you to secure a cloud environment. Thank you so much for your time. I hope you found this informative. If you have any questions, let me know. I'll be online in the hallway.